All right, so this is lab number 5, magnetic braking with Faraday. All right, so our purpose was to collect the data, so like the time of a magnet falling through a conductive tube of aluminum foil and observing how long it takes to apply the concepts of flux, Faraday's law, and Lenz's law, and then create a computational model and compare it with our observational data. All right, so the basic fundamental principles we used were the Bois-Savart law, which is about the magnetic field. We also used the Faraday's law, which is the EMF is the derivative of flux. Lenz's law, that the magnetic field generated from an induced current is opposite to the change in flux, and then the magnetic force through a wire. Oh, and also magnetic flux. So the results is the experimental time was 1.51 seconds, and the computational time was 1.65 seconds. So a pretty slow free fall. So the procedure for the physical part of the experiment was you use a roll of aluminum foil, then you take the dimensional measurements of it. You determine which side of the magnet is north, and then you drop the magnet through the tube and record a video so that you can accurately get the time. And then you do this 3 to 4 times and average it out to get a more accurate result. So the data is the tube was 0.3 meters, the width of the tube was 0.006 meters, inner radius 0.02, and then the mass of the magnet was 0.021 kilograms. Magnetic dipole moment was 3.4. So the trials varied a decent amount, and the average was 1.51. So the observations is the magnet falls slower than it would in free space. It's kind of freaky to watch. And then the downward force on the magnet had less magnitude because the cylinder foil applies an upward force on the falling magnet. So some assumptions is the system only contains the aluminum foil and the bar magnet. So that's excluding all the wires in the room. All right, so now the coding section. The first thing I did was initialize the graph and some basic measurements of the magnet and tube. From there, I created the tube and the magnet. And then after that, I made a program that uses a version of the Bois-Savart law, and then another one that takes the derivative of the flux to get the current and forces. And then this is the code for the simulation. All right, so the code results. This is the time, or not the time, the graph. And as you can see, the computational model spit out a value of 1.65 seconds, which was slower than the actual time. So analyzing the computational model, this is a screenshot of the computational model. And the red and blue in the tube are currents flowing in opposite directions. And the north end was pointing downwards when it was falling. And because the mag field points out of north, the magnet was getting closer to the loop. There was greater magnetic flux in the downward direction of the loop. And then the induced B fields points in the opposite direction of the change in magnetic flux. So sources of error, human error. So most of this lab was using technology, so there is very limited error, but there could have been slight mismeasurements, and mismeasurements with the times. Also, maybe dropping the magnet not perfectly in the center could have a slight effect. So what if the resistivity of the conductor was reduced as close as possible to 0? So the induced current would increase and approach infinity due to Ohm's law. Due to this increase in current, the magnet would take way longer to fall through the tube. And then what if there were holes and slots cut into the tube? There would be less rings in the model, and this means less loop area, meaning lower magnetic flux.